In this session, I will discuss the problem statement on wing design. The problem statement is to design a wing for normal category GA aircraft with the following features. Wing area S equals 18.1 meters square, mass M equals 1800 kgs, cruise speed or cruise velocity equals 130 knots at sea level, stall speed Vs equals 60 knots. Assume that the aircraft has monoplane high wing with split flap. Let's begin with the solution. In this problem, NACA airfoil is selected. The airfoil selection calculation for the wing is: first, we'll calculate the ideal lift coefficient. First, calculate cruise lift coefficient CLC. In this equation, as we know, weight W equals mg, m value is given, and g value we know it's 9.81, and the density at sea level value is 1.225. Cruise speed Vc is also given, it's 130 knots. To convert knots into meter per second, you need to multiply 130 with 0.514, and the wing area is also given, it's 18.1 meters square. So after solving this equation, you will get the value of cruise lift coefficient as 0.356. Next, wing cruise lift coefficient CLCW equals cruise lift coefficient divided by 0.95. Substitute this value here and you will get the wing cruise lift coefficient as 0.375. Finally, ideal lift coefficient CLI equals wing cruise lift coefficient divided by 0.9. Substitute this value here. After solving this equation, you will get ideal lift coefficient for the wing as 0.416. Next we'll solve maximum lift coefficient CLmax. Here weight, as we know, it's m into g. So mass value is given and g value is 9.81, and density at sea level is 1.225. The stall speed is also given, it's 60 knots. To convert knots into meter per second, multiply 60 into 0.514, and we know the wing area, it's 18.1. Solving this equation, you will get maximum lift coefficient as 1.672. Next, we'll calculate wing maximum lift coefficient CLmax W. So it's CLmax divided by 0.95. Substitute the aircraft maximum lift coefficient value here and solve this equation. You will get wing maximum lift coefficient as 1.76. Wing airfoil gross maximum lift coefficient CLmax gross equals CLmax wing divided by 0.9. Substitute the wing maximum lift coefficient value here, and the wing airfoil gross maximum lift coefficient CLmax gross value we get is 1.95. As mentioned in the problem statement, the aircraft has split flap. The lift increment coefficient generated by the split flap is 0.45 when deflected at 30 degrees. Therefore, maximum lift coefficient equals wing airfoil gross maximum lift coefficient CLmax gross minus lift increment coefficient by the split flap, which is 1.5. After substituting the values, you'll get the wing airfoil net maximum lift coefficient CL max as 1.5. First, we need to find NACA airfoils that provide ideal lift coefficient of 0.4 and net maximum lift coefficient of 1.5. From this figure, these 7 airfoils whose characteristics match to our designing requirements, CLI and CL max values are selected. Now, all we need to do is to compare these airfoils to identify which one airfoil is best as shown in the table. By comparing the numbers in the above table, we can conclude that NACA 64415 airfoil is the best airfoil in terms of 3 features, that is, it has high CL max value and high CL by CD max value and low CM naught value. Figure shows characteristic graph of the selected airfoil 64415. In this graph, the horizontal axis represents section angle of attack and the vertical axis represents section lift coefficient. The ideal lift coefficient of the airfoil is calculated, that is 0.416. The corresponding angle for this ideal lift coefficient value is 1.9 degree, which is the wing setting angle. As mentioned in the problem statement, the aircraft type is general aviation aircraft. From this table, the aspect ratio is selected to be 7, no twist is assumed, and the taper ratio is assumed to be 0.3. From trial and error, the following wing specifications are found to be satisfying the designing requirements. Those are aspect ratio equals 7, taper ratio equals 0.8, twist angle alpha t equals minus 1.5 degree, and wing incidence is equal to 1.86 degree. One is the wing geometry created in XFLR 5 software, and figure 2 shows lift distribution of the wing geometry created in XFLR 5 software. Takeoff speed of GA aircraft is about 20% faster than the stall speed. Therefore, takeoff speed VTO equals 1.2 times the stall speed Vs. After substituting the value, we'll get the takeoff speed as 72 knots or 37 meter per second. Calculate lift coefficient during takeoff, CLEO. In this equation, VTO value is substituted and the other values are the same. After calculating this equation, you'll get lift coefficient during takeoff as 1.161. As indicated in the problem statement, the wing has split flap, so we need to determine flap chord, flap span and flap deflection during takeoff and landing. Initial flap parameters are selected as follows. The flap chord is selected as 20% of the wing chord, that is CF by C equals 0.2. Here CF is flap chord and C is wing chord. 20%. Flap span is selected as 60% of wing span, that is BF by B equals 0.6. BF is flap span and B is wingspan. The flap deflection, that is delta F, is set to be 13 degree. When the flap is deflected at 13 degree, the airfoil stall angle is about 12 degree. For safety, takeoff wing angle of attack, that is alpha TO wing, is selected to be 10 degree. By trial and error, it is estimated that by reducing wing angle of attack to 8.88 degree, the wing will generate a required lift coefficient, that is 1.16. Wing has wing setting angle of 1.86 degree. The fuselage is pitched to 7 degree during takeoff. Fuselage takeoff angle of attack equals wing takeoff angle of attack minus wing incidence, that is 8.88 minus 1.86, which equals 7.02. Incidence will be 1.86 degree. Wing takeoff angle of attack is 8.88 degree. Fuselage takeoff angle of attack is 7.02 degree. Flap deflection at takeoff, delta FTO equals 13 degree. Parameters such as wingspan B, root chord CR, tip chord CT, and mean aerodynamic chord MAC are determined by solving the below equations. Aspect ratio equation, as the aspect ratio value is known and wing area is known, you can find out wingspan by solving this equation. You can find mean aerodynamic chord, which is equal to 1.6. The mean aerodynamic chord equation, you can find out the value of root chord. After solving this equation, you will get the value of root chord as 1.78 meter. Ratio formula, you can find out the value of tip chord. Taper ratio is known and the root chord value is calculated. So solving this equation, you will get tip chord as 1.42 meter. Parameters are also calculated. In the initial flap parameters, flap span BF by wingspan B was taken as 0.6. Solving this equation, as the wingspan is calculated, the flap span we get is 6.75 meter. Similarly, the flap chord to the wing chord is taken as 0.2 in the initial flap parameters. So after solving this equation, you will get the flap chord as 0.32 meter. Shows the top view of the half wing with all the parameters. Shows the side view of the aircraft in cruising flight. And the last figure shows the side view of the aircraft during its takeoff. This completes the solution of the problem statement. With this, I will end up this session here. Thank you.